Thank you for inviting me to talk, Susan. What we're going to talk about a little bit today is a basic overview of what our hub architecture looks like, the history of our network architecture, a lot of the issues that drove us to install MPLS in the first place, some of the challenges that we faced back then and some of the challenges we still have today, some specific experiences with our VPN deployment, and some other neat stuff that makes some of our other tasks a little easier, like IPv6 deployment. It's our basic hub architecture. This is a hub topology diagram that describes the architecture. The basic components of this are a redundant component WAN layer, which provides the backbone transit as well as the backbone entrance for local devices. There's a redundant component core layer, which provides for the aggregation of all the edge devices, and then all the edge boxes themselves, which are somewhat role-oriented, although the roles are somewhat more general than they were a few years ago. The ARs, or the access routers, provide the role of aggregating all of our internet access customer terminations as well as peers. The PRs, or private routers, perform the role of VPN customer termination, and the route reflectors are dedicated route reflectors. From an MPLS perspective, all the tunnels begin and end at the CRs. The access routers and RRs don't have any tunnels on them whatsoever. They forward all their packets with native IP forwarding up to the core. Once it gets there, that packet is wrapped into a label and then switched into the WAN layer. And the WAN layer plays the role only of a label switch router and doesn't have any tunnels terminating on it. The 3D diagram here represents just a basic concept of how our WAN layer interconnects with some of our various pieces of transmission equipment. For OC48 and above, we connect directly down to the DWDM, bypassing SONET. And for OC12 and below, we connect directly to the SONET protected rings, which of course uses the DWDM gear as a foundation. We move up the architecture a little bit into the core and edge. Actually, this is an extra slide. One of the hazards of having to submit your slides a week in advance. This is the right one. For a hierarchy of edge to core and core to WAN is always maintained, even across transmission boundaries. Let's see if I got a mouse here somewhere. Here it is. Oh, this is good. I got it. So if you've got an edge device sitting over here in POP G, he's going to want to connect to a core layer in some other POP A. And if you've got another POP Z, that's got edge routers and core devices in it, you're going to want to have it connect directly to a WAN layer as opposed to a core layer somewhere else. The danger in violating this architecture is that, let's say you take your POP G with you just got an edge box down there, and you bring it all the way down into your WAN layer somewhere. By virtue of the fact that your MPLS core mesh starts at your core routers, your traffic is going to be natively IP routed through the core instead of traffic engineered on MPLS like you want it. And of course, having some native IP on all of your trunks isn't truly bad. It doesn't represent any real threat to the customer's performance or connectivity or such, but it does undermine the integrity of whatever RSPV bandwidth values you have set on your circuits. In order to understand why us crazy people at Global Crossing were crazy enough to put MPLS on it in the first place, it really helps to have a history of the network and how it evolved and what challenges we were trying to solve. Back in 1998, when Frontier acquired Global Center, the Global Center network was an as-of-yet unmerged collection of 3 networks: PrimeNet, ISI, and FrontierNet. In all these cases, the core transport technology used was third-party ATM transport purchased from a variety of carriers, including MFS, WorldCom, and Frontier. With Frontier's nationwide fiber network still in deployment, Global Center had the opportunity to build a greenfield network on it, but faced a real difficult struggle to bring its legacy networks onto that network. The first task was to merge all 3 primary ASs into a single AS, AS3549. And once we get that complete and some of the first hubs and backbone links of the new network went into production, then that's where the real difficulties started. Local loops to get our legacy hubs and traffic onto the new core took months to get installed because of varying lead times and different speeds of circuits. Our strategy was to order a whole bunch of circuits at once. We ordered a whole bunch of DS3s, a whole bunch of OC3s, and a whole bunch of OC12s. The DS3s always came in first, about 30 to 60 days. Then we got a handful of OC3s about 90 to 120 days later. And then our OC12s are taking anywhere in the neighborhood of 6 to 12 months to get installed. So the resulting mess in our metro areas proved extremely difficult to manage with IGP metrics. Later on, major pops such as Sunnyvale 2 came online with dark fiber, and we had direct wave OC48 connectivity into the pops, which reduced some of our need for MPLS. And at this stage of the network, we'd accomplished Ed Kern's original solution for traffic engineering: just add more bandwidth, don't use MPLS. But we were already pretty comfortable with MPLS at this point. By May of 2001, Global Crossings Network was a clean set of redundant OC48 links and express paths. And then our network today touches every major region of internet activity, including 8 major hubs in Europe, 3 in Latin and Central America, as well as facilities in Japan, Singapore, Korea, Hong Kong, and Australia. In addition to the complex mesh of metro circuits that we had and the desired traffic engineering capabilities, hop count during this state was also a big issue for us. Because our legacy networks tended to connect at the edge of the core and then transit it, certain paths such as, for example, Burbank, California to Washington, D.C. would incur as many as 18 hops, with other providers at that time having about as many as 16 hops in their network. Windows IP stacks were breaking all over the place as our TTL limit of 32 was exceeded. So initial engineering workarounds included using some GRE tunnels on 7500 platforms to bridge the gap and get the packets across the network. But clearly this wasn't a good long-term solution. And also the GSR at that time did not support GRE tunnels, so we couldn't really build a GRE mesh inside the core. We had to do all of this at the edge, popping over the core. And also back at that time, we were also thinking that someday we might want to deploy one of these newfangled MPLS-based VPNs, so we thought maybe MPLS might be a good way to go, and certainly factored that into our architecture and design. So some of the band-aids that MPLS provided for us. When we learned that MPLS was in the early testing phases for the GSR and supported cool options like no decrement TTL, we started to see a viable solution emerging for our hop count problems, and also MPLS's ability to find the needed bandwidth for an LSP through these odd mesh of metro circuits was just what we needed to cure our IGP blues. Our first implementations of MPLS were pretty limited. We started out just solving our basic problems, establishing some cross-country tunnels across the core to mask all those hops that were showing up, and then also took advantage of the traffic engineering capabilities in a few limited metro regions where we had the most difficulties. Global Crossing believed this theory that if you got multiple suppliers, you've got best of breed. And plus, if you don't like vendor A, you've got contingency plans. You've got a relationship with vendor B. You can always switch to them if the going gets too rough. Well, in reality, once you've invested a lot of capital in a vendor, it's really quite impossible to replace all of that with another vendor. So much for the backup plan idea. And as far as best of breed is concerned, you don't have best of breed, you have worst of breed, because now when you want to deploy a new feature, you can't just deploy the implementation of the first vendor to get it done, but you have to wait for both of them to get it done, and to get it done in a fashion that's compatible and interoperates. Differing interpretations of the early MPLS internet drafts were the cause of some of our earlier bugs and issues that we found. For example, the penultimate hop problems, when different vendors played the core and WAN layer roles in a POP. One vendor interpreted the draft to mean that the penultimate hop should pop the label and forward the packet natively, while another thought the IP packet should be wrapped in a null label. This resulted in some dropped packets, like maybe 100% or so. Another interesting problem was a difference used in the logic to accomplish hop masking. An example was that if Cisco was at the head end of the tunnel and a Juniper was at the tail end, the Juniper would take the TTL field of a label and copy it into the TTL field of the IP packet upon de-encapsulation. This had the effect of resetting the TTL to an extremely large value that was not likely to reach 0 before it reached the destination. So the result was that once a traceroute, for example, entered the LSP, the next hop was the final destination. True one-hop network. Traceroutes typically looked like 3 or 4 hops to any location on the internet you wanted to go. Our marketing folks thought this was really cool. The operations team didn't quite agree, though. So Juniper was nice enough to add some knobs for us to allow the intended behavior of this feature. Some of the current issues that we face from an interoperability standpoint include fast reroute, having compatible implementations, also stability in the code that is currently available to perform these functions, secondary LSPs to back up your primary ones, and also something that we're looking to do is auto bandwidth across both vendors. A couple of stats on what we've got right now. Our MPLS core mesh has got 9,900 tunnels that make that up. And then for our VPN product, the slide says 1,200 tunnels. That was the case late last year, but it's currently looking about 500 to 600 tunnels right now. Once the secondary LSPs are deployed, that number will get bumped back up to 1,200 in the future. So that's a total of about 11,100 tunnels total in the core. And as you can imagine, with this many tunnels, it's really quite complex. So we had to write some stuff to handle that complexity. One of those was what we affectionately call the MPLS robot. The components of the robot's got a high-speed SNMP polar to go out and collect data. It's got a tunnel resize script. It's got a whole ton of knobs to control how you resize your tunnels and RSVP tunnel bandwidth settings, a graphing capability, and of course a bunch of push scripts to get all that stuff back out to the routers. And then it's almost really a separate product. There's a path database involved in that as well. And that features an SNMP module for collecting Junos path data, as well as an expect script for getting the Cisco data. It's got a relational database backend, an XML module for extracting configurations, and a prograph module for offline Dijkstra SPF calculations. So the application takes all the data that it gets, and then it goes out and it uses the Dijkstra SPF runs to calculate what the best route would be and make some comparisons about your LSPs. Are they using the best route or not? So you can get some data like, well, 90% of our LSPs are taking the most optimum path. The negative with that is that it's making an inherent assumption that your IGP metrics are all correct and that it's got that the IGP actually reflects the true best path. We also use this thing called WANDL, Wide Area Network Design Lab. We use the IP MPLS module with WANDL, and basically what it does is it takes the iOS and Junos config files and crunches them into your traffic demand files, which are used by WANDL for the simulations. And what it's primarily looking for in those configs, in addition to the network topology, is the RSPB bandwidth values of each of the tunnels, and it uses that to create the demand files. Then you can take those demand files and tweak them to add your additional demand information for your simulation, or you can leave them as is and do your failure analysis just like you would if you're using WANDL for native IP. The tunnel traffic data does provide some very unique data that's difficult to get from native IP, namely CR to CR traffic flow values, and by having that, it really makes this job a lot easier, and you can have a lot more confidence in the output that you get out of the simulation. So let's say that you wanted to think about being crazy too and deploy MPLS. This is sort of a history of how you get started down the road of implementing MPLS and what this plan looks like. You want to look for features of your network design that might make it real hard for you, or at least make it more difficult than it could be otherwise to implement MPLS. Stuff like multiple ASs will require you to have the inner MPLS features enabled and working in order to do a wide-scale deployment. Multiple levels or areas, stubs in your IGP will make it more difficult, requiring some LDP work. And lack of TE support in your IGP would be good too. So if you're using RIP, you might want to upgrade. So in order to get started, you first have to go through and enable RSVP on all your interfaces. You don't want to enable the maximum because you don't want to overload your links, but you do want to set some reasonable number between 0 and 2.5 gigs on there, so that some tunnels can be routed over it. And then when you're setting up your tunnels, you start out by setting them to basically have a size of 0. And because there's no quality of service or policing or anything, this isn't going to cause any problems. But what it does do is enable packet forwarding into the tunnel, and then you can go and measure that over 24 hours or a week or what have you, and then decide how much bandwidth you want to reserve for that particular router-to-router pair. So not only do you want to set that up, but you also want to include a little fudge factor in there. You don't want to set it exactly to your P95 values. You want to give it the ability to do some burst and have some protection. Also do your tunnel implementations slowly. I would not recommend rolling out 11,000 tunnels on your network in a single maintenance window. You should probably stage that a little bit. So roll it out in a couple of metro regions and slowly step it up until you have your full topology that you want to have in place. And then, of course, you can tune your RSVP bandwidth values on all of your circuits as you're starting to see more and more traffic become MPLS switched instead of natively routed. A little bit about our roadmap. We started trials in the fourth quarter of 1998, just in the lab, of course, mucking around with a bunch of 2600s and whatnot. In the first quarter of 1999, we really started to do production trials in the network, mostly to solve our short-term problems. So, as you can see, we've been doing this for quite some time now. In second quarter, we officially announced that we had completed our national mesh between all of our core routers. And in second quarter of 2000, when we really more as a result of actually deploying the network and being purchased by Global Center and becoming a global company, we extended that mesh to include the whole globe. So you could do a trace route from Europe to Tokyo and have the entire U.S. apparently skipped in the trace route. And then second quarter of last year is when we finally rolled out the RFC 2547 IP VPNs and Layer 2 VPNs, along with some DISRV. So all the way through 1999 and some part of 2000, MPLS got blamed for an awful lot of our problems. Operations blamed it, and engineering blamed it. And there were a variety of issues that we found: high latency, loss, reachability issues, and the workarounds for this usually involved, well, if a tunnel stopped forwarding, you'd bounce it. And what this really had the effect of doing is resetting the forwarding table so that Ceph would recalculate. Almost all these workarounds were to resolve Ceph bugs. I do recall a time sitting out in the Cisco office in Chelmsford, Massachusetts. We just had a week of just terrible packet loss. It had been a real awful time, and we were beating up the vendor, why does your MPLS implementation with so many packets? And they swore up and down, Dan Tappan shaking her head, no, it's not my code, I didn't do it. And after several hours of this, Cisco insisting that we must have changed something the weekend before to cause all this, an engineer raised his hand in the back and said, well, I did do something, but I don't think that it could have caused this. He deployed weighted red, hadn't told anybody. Clearly this wouldn't happen today. We have very mature change management processes in effect, and a planning process that would keep everybody very informed about what was going on, but the organizational processes weren't as mature back then, so stuff like this was allowed to slip through, and improperly configured weighted red does, well, any implementation of weighted red will drop some packets. I think it goes without saying that operations groups need a lot of training. Clearly, this adds a dimension to that training experience, and new training materials have to be created. And then, of course, there's just no replacement at all for having true experience in your operations center to handle this. Because we have been doing this a long time, one benefit that we had before we rolled out MPLS-based VPNs was our operations group already had 2 full years of experience with MPLS from a core perspective before they had to dive in and deal with VPNs. It's also interesting that while our core NOC is currently in the process of cross-training some of the ATM guys to do IP and the IP guys to do ATM, that we hear remarks such as, oh, this ATM stuff is a lot like MPLS, and oh, MPLS is kind of like an ATM Lite. There are a couple of conceptual similarities, but obviously stops about at the conceptual level. But clearly, the operations hassle of training everybody to work with MPLS really isn't as impossible or as expensive as some people thought it would be. A couple of notes on our express route architecture. This is our IPVPN product. One of the objectives was to provide as much isolation from the internet as possible while still leveraging the bandwidth in our core. So we chose to use a separate autonomous system number that's not advertised. The private routers are not reachable from outside of our network. The address space is not advertised. There's a full mesh of LSPs between all of the PRs, and there's also a full IBGP mesh among all the PRs. We don't have a requirement to use route reflectors at this point, with only 25 private routers out there across the globe. In our lab testing, we baked off Cisco and Juniper, and we ended up selecting Juniper routers for a private router, based in part upon their VPN roadmap and some capabilities they had, such as the CCC capability and the L2 VPN roadmap. But we also found in the lab that for testing from an RFC 2547 standpoint, and keep in mind this was quite some time ago, maybe as much as a year and a half ago, the Juniper proved to be much more scalable in terms of number of VRFs and number of routes in those VRFs that it could support for 2547. By like 2 orders of magnitude more VRFs. I'm sure Cisco solved that by now. A secondary objective is to provide as high a class of service as possible. So there's a couple of things we do here. The LSPs themselves that start at the private routers have a higher priority than LSPs for the internet service, so they always get the best path through the network. And also we paint all the TOS bits into a business class, which is then rewritten into the XP field as it goes across the core. So all of our VPN customers have preferential treatment in the queues versus the internet customers. An interesting case of your product line, when we have a customer that purchased an IP VPN between South America and the United States, and then purchased an internet connection to us in the United States so that he could get the priority bandwidth between South America and the U.S., and then bought regular internet service. This is sort of the profile of the VPN customers that we have today. It's pretty much an even mix of RFC 2547 and Layer 2 customers. The sales funnel, on the other hand, I would say the majority, not by too much, about 60%, they want to have the RFC 2547 style VPNs. And the largest customer we have installed today is an RFC 2547 customer with approximately 50 circuits. However, one of the customers is currently in provisioning, has got more on the order of 800 circuits. And clearly the market interest is still gaining some momentum for this product set, particularly enterprise customers. I don't think they really understand what an IP VPN can provide for them, or why they'd want it, or why there's value, even though it's so much cheaper than things like frame relay. So the sales cycle for these customers is very long, maybe 9 months to a year before you can really close the deal. There are some major differences between the L2 VPNs and the RC2547 VPNs from a provisioning standpoint. They are both extremely complex and verbose in their configurations, and there's simply no way to do it without having a automated tool to generate those configuration snippets for you, which we do have. It's called Sniper. I think that somebody was thinking of shooting someone at the time they wrote it. I couldn't say who. But Sniper basically allows you to take a customer design and map that into all the points they want to go on the network, and then generates all your configs that you can then push out to the routers. Some of the differences in just the way that our provisioning group prefers to do things. The L2 VPNs are really easy from a setup standpoint. Customer says, I want L2 VPN. We say where, we configure it. It's really straightforward, and the customer can push whatever they want over that L2 VPN, and it just doesn't bug us at all. But the difficulty there is that if after the provisioning is complete they want to add another circuit into the VPN, you not only have to update that one circuit, but you have to go and update every other interface that's part of that VPN, such as adding a Delcy or whatever that cross-connects into the LSP that goes to the other routers, and this can be a bit of a hassle. The L3 VPNs, on the other hand, is a little more automated. You attach the customer's interface into the VRF, and the BGP magically does all the rest for you and distributes the VPN information. But one of the issues that we see is that L3 VPNs, because as an ISP you have a much more involved role in the routing for the customer, you have to have some knowledge about the way their existing network is built and exactly what they hope to get out of having the service. So what we've seen is we have a lot of these customers coming in, and they don't want to bet the farm on IPVPN or MPLS-based VPNs, but rather they'd like to use it as a backup solution for their existing frame relay network, which they obviously are quite comfortable with. But this customer could be running a whole bunch of stuff. He could be running EIGRP, for example, and that might not be something you want to run in this VRF on your Juniper. So you would encourage them to maybe upgrade to OSPF, and we've helped customers to transition to a better network topology that's going to work a little more cleanly with the VPN. So this sort of situation really highlights the importance for the customer network engineering discussions to take place both pre and post sales. In this particular case, we helped them redesign, and probably are looking at a lot more of that for these types of customers. Now, once a customer is up and running on the network and he tests out his IPVPN and fails over to it and finds out that it rocks, they tend to leave it there and they make the frame relay network the backup. So that's a good thing. When we decided to deploy some limited IPv6 capability to mess around with it and make it sort of an unofficial product, we rolled out a few routers to some of the native exchange points, and like everybody else, sure, we could have just done GRE tunnels, but hey, we got MPLS, so we'll use it. And some of the cool stuff this does is per tunnel utilization statistics. I know exactly how much this router is sending to this other router. It also tells me the exact path through the network. And it's pretty scalable in a sense, not just in terms of having the overlay and being able to add routers into the mesh very easily, but I can be pretty confident that it's not going to affect anything else on the network. So, basic question. If we had the network that we had today, but we were using IP forwarding, would we still want to make the leap to MPLS? Well, the modeling has indicated that we don't need MPLS for traffic engineering right now, but the architectural benefits of having a 100% MPLS traffic engineered network are valuable for MPLS-based VPNs. From the reverse point of view, We don't perceive there to be any value in going back to simply doing native IP forwarding either. Between being able to give VPN customers priority routes with the lowest latency, prioritize traffic for the lowest latency and guaranteed performance, and knowing the exact route their traffic takes, there simply wouldn't be any sense in revamping the network without MPLS. So to summarize, we like it. We've been using it for a long time now, about 3 years, and it's comfortable. It's become a part of our operating environment, and, well, we're used to it. So, as always, the usual disclaimer, your own mileage, it might vary. Any questions? What's that?
I think there are no questions. Dave, thank you so much.
Go ahead. One more page. I did want to take a moment to thank a few people, not just you guys for putting up with me, but the deployment at Global Crossing has not been a one-man team effort. It's involved a whole ton of people, but clearly there's a few people that stand out as having a real important role over the past 3 years in MPLS. In the early deployment days, Alan Hannon, Dr. Siping Zhao, Dave Cooper, Brooke Bailey, and Steve Carter all played real critical roles in helping us get this rolled out. For ongoing feature enhancements, Dave Cooper and his research and development team, Mark Bath, ongoing iOS and Junos, bug management and feature testing, regression testing, Brooke Bailey and Scott Blair. And from a traffic engineering perspective, these guys have done a tremendous job. Denver Maddox and his team, including Matt Meyer and Steve Scheck.